some mistakes when I did this the first time around, so I didn't even include number 6 and number 7. I also wanted to call out that, again, I did make some mistakes on number 1 and lateral area, total area, so just make sure you are looking at the YouTube for the first video because the correct answers are written there. And also the volume on number 5, I think, is silly error where I didn't do the height of the cone. I used the slant height as the height of the formula. 1/3 base area times height. So that was a mistake. So this I think should have been 324 pi. Anyways, I didn't include number 6 and number 7 in there because, hey, I misinterpreted these problems the first time through, and I made a silly mistake on number 7. On number 6, and number 7 is actually a little bit harder to think about what exactly these are doing. So anyways, I not only did I make mistakes in these, I've actually already filmed another video including 6 and me going over 6 and 7, and that video didn't save correctly on my computer. So because of that, I'm a little bit frustrated by that, so I'm probably going to go through this pretty quickly. Please email me if I went through this too quickly and you still have questions. But anyways, number 6, that was the easier of the two. I'm guessing fewer people are going to look at those. So let me go through that, and then I'll go through number 7 right after that. Number 6, we got the total area of a cube is 2,400 square meters. So normally when we have squares, right, we need to take the square roots of the area of the square to get us to a side length. So I'm going to label this as S here and S here because getting a side length is really important. It's really, really helpful to you getting volume because we don't have a volume postulate in the textbook. They're like, let's just not bother with the volume postulate. I think you get the point. But if we did have a cube postulate, right? If we had a cube postulate, this would be our first assumption here, that the cube's volume is just going to be its side length to the third power, because side times in another dimension, right, depth here being side, is going to be the way you can get volume. Length times width times height, or width times length times depth, or however you want to call it. There are 3 dimensions in space. That's how you get volume. Okay, so then the question is, how do we get S? We have an area calculation here, but is this the right area to allow us to solve for S? And the answer here is no, we need to change things. So just a reminder of what a cube is, right? A cube is, well, let's get to the fancy Greek name for cube, right? Because a cube is one of our special solids. It's a platonic solid. It's one of our 5 platonic solids. Anybody remember what that's called again? Which of the 5 platonic solids this is? Well, it's regular. I mean, all of the platonic solids are regular polygonal faces, and this regular polygon is a square. So it's a regular what? How many sides does it have again? Oh, it has 6 sides. So we got to use the Greek prefix for that, which is hexa, right? Hexagon. So the sides aren't hexagons, but we're going to call it a hexa because that means 6, and hedron because that means sides, and it's the singular for the amount of shapes. A 6-sided figure, or a 6-faced. Hedra actually means faces, and hedron means a single figure with a certain amount of faces, and that being 6 faces is the figure, this hedron. And hedra is the plural. So if you had several cubes, you'd be like, look at all this great hexahedra right there. Okay? So the key to this problem here is that you're given the 2,400 square meters as the volume as the surface area for the whole cube. And remember, a cube has 6 sides. So what you need to do is you need to get the area of just one of those 6 sides. For instance, if we knew what the area of this is, then that's great because we would just need to take the square root of that area to get either of these dimensions, the side lengths here. So S times S gives us the area. So if we can figure out what the area of that is, and the area down here, for instance, is going to be just this divided by 6. We need to find this as a unit rate, right? 2,400 divided by 6 is going to be 400 square meters for one of those sides, or 1 square of the regular hexahedron. Okay, so this being said, this is pretty easy now. You've been doing this for a while in your math studies, that the area of a square is what's on the inside, and then to get the dimensions, you just need to take the square root. And the square root of 400, right, the square root of 4 is 2. The square root of 100, right, and 4 times 100 is 400. The square root of 100 is 10, so 20, right? 20 would be the length of one of the sides. So this would equal 20. Okay, so that's going to get us to volume. Finally, we can get to volume up here, and volume is going to equal 20 to the third power, which is 8,000. So we got 8,000 cubic meters. is our answer to 6. Okay, number 7, we got a solid with metal cylinder. It has with radius of 2 and height of 2 is recast as a solid cone with radius 2. Find the height of the cone. Okay, so this here, I just gotta get this quickly because I gotta get this over with. This sort of reminds us of what a solid is. Remember, a solid, just going through super quickly, a solid includes all the volume in between. Okay, that's different than like a circle or a hexagon or any of the shapes you look at. So the shape doesn't include its area, but the solids, any kind of solids we study, so that goes for like cones as well, it includes its volume as part of the shape. So what we mean by solid metal cylinder is just a cylinder, right? A cylinder made up of metal like this. It's melted down, right? Melted down and recast as a cone. So in this problem, what you're looking for is you're looking for volumes are the same, because it's a three-dimensional shape that's getting recreated as from one shape to another shape, and three-dimensional shapes are measured by their volume. Volumes are the same. All right, so do you see why the volumes need to be the same? This is a solid metal cylinder, and if we melt it down and then make another shape, it's going to contain the same amount of space. So that's why the volumes need to be the same. So I'm going to erase this right now before we get into this problem here. Oops, looks like I can't erase. But the idea is that volumes are going to have to be the same, so I can't, it's not letting me erase right now. So I'll just have to continue on with the problem. More frustrating than usual. So anyways, let's just get started with this. Volume of the cylinder is going to equal the base area times by height. And what did they give to us? They give something about the base area? Yeah, they did. They gave us a radius of 2. They gave us a radius of 2 here as well for the cone. So the question is, what is the height of the cone going to have to be when it has the same area to the volume of the cylinder? And did they give us the height here of the cylinder? Yeah, they did. They gave us height too. And actually, hey, just looking and labeling these things, 1, 2, 3, and then we're missing the 4th thing here. Do you have the answer? Do you know what h has to be? Well, check it out. I'm going to do this. I'm going to switch this to 6. That's right. Height of this has to be the 6 in order for the volume to be the same. And I'll solve it fully through so you get the rest of the answer, right? We had 800 cubic meters here. We did the work. We're going to do the work for this one too. Yeah, this one's going to be 6 because, hey, what do you know about the volume of a cone formula? Volume of a cone equals a third base area times by height. And what we see down here is that the base area of these two actually equal the same exact thing. They equal pi r squared, which equals 4 pi, right? They both equal 4 pi. So the base area is not going to matter in a second, because if we're taking the cylinder and we're recasting it, right? We're changing that, taking that volume, melting it, and making it into a cone, they would have the same volumes. And if they have the same volumes, we got the volume of the cylinder is its base area times by height. And let's make this height of the cylinder. I'll put a little subscript there, height of cylinder. And this is the height of the cone. Well, we would need to figure out the height of the cone that's going to give us the same volume as the volume of the cylinder. So we can set the volume of the cylinder, which is base area times by height of the cylinder, equal to the volume of the cone, which is 1/3 base area times by height of the cone. And what we know about the base areas are the same, so we can cancel those out, right? We divide both sides by the base areas. Remember, the base areas are the same because they're both circles with radius of 2, so they're congruent circles. So base areas don't matter in this problem, but the height of the cylinder is going to have to be 3 times larger, or 3 times shorter, right? Height of the cylinder is only going to be 1/3 of the height of the cone. And if we knew that the height of the cylinder, it's substitution time. The height of the cylinder is 2. Then 2 would equal 1/3 the height of the cone, and we can see very quickly, well, if 2 is 1/3 of the height of the cone, we got to multiply the 1/3 by 6 to get to 2. But we can also do it the old-fashioned way. We can multiply both sides by the reciprocal of this 1/3, which is 3, and then we see 3 times 2 is 6, and we're good to go. We got the height of the cone there. So I like that problem. I reread it wrong, actually, and if I showed you the extended video earlier, I thought they were talking about surface area here, so maybe you made the same mistake. Oh, we got to cylinder and we got to recast the surface area to make it a cone. No, solids are solid. They include the points, not just on the lateral faces, they include all the points in between, right? So all these points within the cone, right, connecting to a base, the interior of the base, is part of the solid, right? Part of the solid. So we can think of solid as a not something filled up with air, right, but something that's kind of filled up with metal or filled up with material of some kind. Okay, air can also be measured in volume too, but normally if we're talking about a specific product, we're talking about its volume in terms of whatever product it was used to develop it. So what metal was used in casting something, for instance. Okay, that's explanation of 6 and 7. Hopefully these make sense. Email if you have any questions. Now we've done all the self-tests, it's just on to you to do the chapter review problems and chapter test problems. Thanks, guys.